Motion planning is a field of robotics whose fundamental ideas are beautifully spatial and geometric. One of my favorites is the configuration space. Here is a super simple robot, a link that pivots at a single joint. I'll call it RBOT, short for one revolute joint. Its configuration can be completely described by some angle theta about the origin. A configuration is a fancy way of completely describing what's going on in our system. In this case, the configuration of our RBOT is just angle theta, bounded by 0 and 360 degrees. A configuration space represents all possible configurations of a system. We only have one variable, theta, so our configuration space will be one-dimensional, which is a number line. The important part here is that each point in configuration space corresponds to a unique configuration of the RBOT. Here, I'll add a circle to represent an obstacle in our workspace. This obstacle will limit the set of angles our robot can reach. We can encode this limitation in our configuration space, the number line, by making a line segment on the number line. Now we have this one-dimensional space where we can clearly see where we can and where we can't go. This is what's great about a configuration space. Collision checking is baked into this space as a line segment. Planning a path for our RBOT is as easy as finding a continuous path in one dimension, picking a start and goal angle, and avoiding the line segment. Let's move up a dimension with our 2R robot arm, a robot with two links and two joints. I'll plot the configuration of this system as a two-vector, theta and phi, because we need two numbers to completely define any configuration this robot might take. This time, we can plot configuration space on a Cartesian plane, with theta on the x-axis and phi on the y-axis. The angles are still limited to 0 to 360 degrees, so they wrap around our diagram. Where it gets really interesting is what happens when we add obstacles into the picture. Instead of line segments like we saw in the number line, we can plot entire areas on our plane as inaccessible by our robot. As I intersect these obstacles, watch how our configuration, as plotted in C-space, moves into and out of these regions. Essentially, motion planning is the computational problem of moving your robot from a start to a goal by finding a sequence of valid configurations between the two. The C-space helps do this by distilling a complex, time-varying motion problem into what becomes connecting dots between locations in C-space while avoiding obstacles. Here, I'll trace a path around our square obstacle in C-space to get a sense for moving around these obstacles.